Okay, looking into section 11.4, this one's very, very short, so this will be a short video here. Just continuing on with those polar coordinates, but looking at equations in polar coordinates rather than just points. Section 4 is mostly about symmetry tests. So this is seeing if something is symmetric in polar equations and not just in rectangular equations. So symmetry tests for polar graphs. Okay, so when we're talking about symmetry, we're still looking at the x-axis and the y-axis. We need to know if it's symmetric, and there's three different kinds of symmetry. The first one is symmetry about the x-axis. So if you fold it over the x-axis, does it all match up? So to test if something is symmetric about the x-axis, this is true if those points that we were looking at, those r thetas in polar form, if these things lies on the graph, then two other kinds of points also lie in the graph. r negative theta, and also negative r pi minus theta. Okay, so if just you have some generic point r theta that is on the graph, then r negative theta and negative r pi minus theta also have to be on the graph. So let me pull up Desmos here and I'll kind of show you this. Okay, so here in Desmos, I graphed 2 points. So here's the graph 2 pi over 3. That point, that's the green dot here. So remember that is going to be a distance of 2 from the origin and then at the angle pi over 3. So here on this angle line pi over 3. And then I also graphed 2 negative pi over 3, which is this purple dot down here. So that's going to be 2 units away from the origin and at negative pi over 3 instead. And remember that these 2 points are symmetric about the x-axis just based on the definition we just wrote down. So if I were to reflect the green point over the x-axis, it would land on the purple point. I could do this other one as well. All right, so if r theta is on the graph, this one I just showed you r negative theta, but this one as well, negative r pi minus theta. I'm not going to bother graphing that in Desmos. Just know that that one's true as well. It would give you the same exact location as that other point there. Okay, so moving on to 2, another kind of symmetry that we would care about would be symmetry about the y-axis. So for this one, if we have a point r theta, just again some generic point, doesn't matter what it is, lies on the graph, then you're also going to have these 2 points, r pi minus theta is going to lie on the graph, and negative r negative theta is going to lie on the graph. All right, so we're going to go back over to Desmos and show this one. Again, looking at this point 2 pi over 3, the green one here, if I wanted to graph something that is symmetric to the y-axis, maybe I would graph negative 2 negative pi over 3. Cool. So if I make both the r value and the theta value negative, it graphs this black point right here. So you have to be a little bit careful about how you go about graphing this one. This is on the angle negative pi over 3, which remember is this angle here. But because the r value is negative, I don't actually go in this direction. I go in the opposite of that direction, which is going backwards here to the black point. But more importantly, the green point and the black point are reflections over the y-axis. So if you make both the r value and the theta value negative, you're reflecting over the y-axis. There's one more kind of symmetry that we care about, and that's going to be symmetry about the origin. So symmetry about the origin means that if you reflect it over both the x and the y-axis, it matches up, or a better way of thinking about it is that if you rotate the graph 180 degrees, everything matches up. Same setup here. So if we do have a point r theta that lies on the graph, then you're also going to have the point negative r positive theta and the point r theta plus pi on the graph. And I forgot on the graph up here. On the graph. Okay, again, so just to show you in Desmos here, so this r theta point is going to be our 2 pi over 3. I'm just going to do negative 2 pi over 3. So one more point here, negative 2 positive pi over 3 is this red point. So the green point and the red point are reflections or symmetric about the origin. If you were to take the green point and then turn that 180 degrees, it would match up with this R value. Or you can think of it as if you reflect it over the x-axis and then the y-axis, you're landing on the same point here. So this is what symmetric about the origin means. These are the 3 different types of symmetry that you're going to have for polar equations. Okay. One last thing that I want to write out for you guys here in this section. Another thing that they talk about is the slope using polar graphs or polar equations. So we can find the slope in this form. Remember, the slope is this. It's the change in y divided by the change in x. But we want to know what this slope is when we plug in the polar coordinate here. So in other words, this slope, but plugging in between, or not plugging in between, sorry, plugging in the point r theta. Okay, so really this dy dx should be here. Great. So this is just the definition of the slope. Dy dx, the slope of the curve, but we want to know it at a polar point, not necessarily at a rectangular point. To do that, it's going to be a pretty awful looking fraction. I would not expect you guys to have this memorized. You'll have the formula in front of you, I hope, when you're taking the test, but this is the formula. So it's going to be f prime of theta sine theta, sorry, that plus f of theta cosine theta. That all divided by f prime of theta cosine theta minus f of theta sine theta. So yeah, I know this equation is pretty awful, but it's very simple. So if we just have like a quick example here, if we're given some kind of function, let's say that we're given r is equal to 6 sine of theta. All right, and remember that this was just a circle. So you'd also have to be given a point. And let's say we are at the location, maybe just 0, 0. That'll be fine. Now remember, this is not x0, y0. This is r0, theta 0. So it is at the origin, but it's of that circle. So remember, if I'm here, r equals 6 sine of theta. It's this circle. And we are at this location down here. So I hope you can just see that the slope here should be 0. But let's plug it all into this equation and double check. So to do that, we're looking for dy dx, which is this awful looking thing here. Okay, so first thing that we're going to do, this theta, by the way, is going to be 0, just based on the point that we're given, but that's okay, we'll just do it as is. So first thing is going to be the derivative of f. F is going to be what r is equal to. If r is 6 sine theta, that's going to be your f of theta. So we're going to take the derivative of 6 sine theta, which is 6 cosine, but it's not going to be of theta anymore, it's going to be of 0. That times sine of 0, and that's going to be plus f of theta, which is 6 sine of theta, so 0, times cosine of theta, so cosine 0, that all divided by the derivative again, which is 6 cosine of 0, times cosine of 0, and that's going to be minus f of theta, 6 sine of 0 times sine of 0. Okay, and then if you just do all these, sine of 0 is just 0, so it looks like we're going to have 0 plus 0 up top, and the bottom, this is going to be 6 times 1 times 1, so 6, minus 6 times 0, so 0. So all in all, this is going to give you 0, which is what we expected to get, because, looking back again at the graph, at this location the slope is 0. Now if I had done this maybe here, at this location, then I would have gotten a positive slope of maybe 1 or something like that here. If I did it over here, I would have gotten a negative slope, and so on and so forth. So it's very easy. Just the awful part is the formula and plugging stuff into the formula. But that's it for section 4.